Okay, so now that we've done volumes of solids of revolution, we're actually going to move on to volumes of solids of known cross-sections, or volumes of known base, or it can go by a number of different titles. But basically the whole idea is that we're still given a region bound by one or more functions, but instead of revolving it, instead of the volume being created by revolving that region around an axis, that region now becomes a place where we then construct cross sections on top of it. Okay, so instead of taking this region and flipping it around the x-axis or something like that, that region is now going to be the base for cross sections that are of the same shape. This one is obviously this one's obviously going to be cross sections that are squares, and the squares are going to be perpendicular to the x-axis. Okay. Now, if I wanted to do this same one with, say, equilateral triangles, okay, notice that it's still the same cross sections on this graph right up here, but three-dimensionally it's going to look a little bit different because it doesn't go straight up from there in a square. It goes straight up, it goes sort of slanted up in terms of an equilateral triangle. And you see the fact that the shape, that the solid that is created, all of the cross sections right there are equilateral triangles, and then you can sort of show that one cross section sort of moving through it. Okay. Well, take a note of that shape, and we're going to sort of undo it right now, and then we're going to go back to the squares. Okay, and then I'm going to show you that the same base creates a very different solid if the cross sections are of a different shape. Okay. Now remember, I told you that integration is a means of accumulation. So all we have to do is figure out how to generate a variable expression which represents the volume of one cross section. We need something that represents the volume of that square with an infinitesimally thin width to it. Or we need one that is isosceles triangle right angle down, so side down, or hypotenuse down, isosceles right triangle with a hypotenuse down, or do they have semicircles? Usually it's not circles, usually it's semicircles, but I guess you can do circles. And that, of course, winds up sort of a spheroid with points on the end. And we see the fact that it runs through like that. So these are all geometric shapes, and as such we ought to be able to figure out exactly how to go about getting a representation, a notational representation, an analytic representation, a variable representation of the volume of those particular cross sections, right? All right, let's go ahead and look at a different base. It's the same idea. This base, however, is different, but we can run through exactly the same types of cross sections. Square cross sections as it runs through that area, and of course the volume is generated by adding up the infinite number of infinitesimally thin square cross sections. Or, of course, we can go back to equilateral triangles and generate that solid again, looking a little bit different because the things that are coming up from that base are no longer squares, they're equilateral triangles. Now let's go ahead and look at circles. Okay, and we can see how that volume is generated by adding up the infinite number of cross sections of circles. How about isosceles right triangle with the base with the hypotenuse down? Looks similar to the equilateral triangle. Okay, well, let's go ahead, and now that I've shown you some animations and you can kind of get your head around it, let's go ahead and do some examples. Now this is a worksheet that if I forget to attach it to the email that I'm going to send you with these videos, please email me back. But I'm going to run through these really quickly, okay? But this worksheet actually has a key to it. So just the worksheet and then 4 pages of key. And basically the information that you're always going to need if you're ever going to do volumes of solids with known cross-section is you're going to need to know the area, the base, okay? What defines the base? And in this particular one, it's this. What shape are the cross-sections? And in this one, they're squares. And then you need to know a third piece of information, and for the sake of this particular worksheet, these are all perpendicular to the x-axis. Now, they can be perpendicular to the y-axis, but for the sake of sort of continuity of this particular worksheet, I just put that in the directions and made them all perpendicular to the x-axis. So I've gone ahead and printed out what these regions look like, so let's go ahead and do it, okay? Now this one, this is y is equal to 1/2 x. This right here is y is equal to -1/2 x. And this right here is x is equal to 6. And I want the volume with the cross sections as squares, okay? Well, here's the thing. If you noticed from the animation that I showed you, the only part of the solid that is in contact with the region is always the base, okay? And the width right here is obviously going to be our differential, okay? So really what we need is we need a formula for the area of the face of that prism, okay? And if it's a square, that winds up being very, very easy. If I'm looking at cross sections that look like this, and I have to define the volume with respect to that length, well, a square is very easy because I know it's going to come up off of the page in exactly the same distance that is here. A square has an area of s squared. Okay? Now, I notice that if they're cut this way, my differential is dx. I'm totally bumbling. My variable expression is going to have to be in terms of x. And of course, my limits of integration are going to have to be in terms of, you guessed it, x. So my limits of integration are from 0 to 6. So this one actually winds up being very, very easy. I want to go from 0 to 6, and I want to accumulate basically the side squared times the dx. Well, what's the side in this particular one? The side is just this top function minus this bottom function. So 1/2 x minus a -1/2 x, or just x, right? Or I mean, that's s. So s squared would be that side squared. So this one, and of course it's number 1 on the worksheet, so it just winds up being x squared dx. This variable expression represents the area of the face, the square face of each prism, infinitely thin prism that are cross sections of that solid. And the dx, of course, is that width. And then I'm just going to add up all of the infinite number of cross sections between 0 and 6. So I'm going to get x cubed over 3, evaluated from 0 to 6. Well, 6 cubed is 216, okay, minus 0 over 3. Well, 216 is divisible by 3. It should be. It's 6 cubed. And that winds up being 72 is the volume. And if they give you units, you put units cubed, right? Because it actually is a 3-dimensional shape. So that basically is what happens on that one. Let's go ahead and move on to the next one. This one, okay, this one has a shape which is defined by y is equal to 2 minus x squared, and and the x-axis, okay? So y is equal to 0. So I'm basically, this little hump that's above the x-axis is my region. For the whole entire worksheet, we're dealing with cross-sections that are perpendicular, okay, to the x-axis, okay? And for this particular one, I'm not dealing with squares, I'm dealing with semicircles, okay? Well, semicircles, I know that I have to deal with the area of a semicircle based upon its relationship to this length right here, which we'll call S for every single one of them, okay? Well, S, if you can sort of see if you can sort of see the semicircle sort of coming off the page right here, that length right there is the diameter. Well, we know that the area of a circle is pi r squared. The area of a semicircle is 1/2 pi r squared. But since that's not r, I'm going to have to substitute in, and let's go ahead and combine the pi and the 1/2. The radius is diameter divided by 2. And of course we can call it d, but like I said, we want to call it s, so let's actually scratch that out and put an s. And so what I get for the area formula for the semicircle with respect to its diameter, which is of course defined by this height right here that stretches across my base, is pi over 8 s squared. And you might actually want to, memorize that. Well, here's the thing. I know that I'm running from here to here. Now, if it's 2 minus x squared, I know that this is negative root 2, and this is positive root 2. So I'm running from negative root 2 to positive root 2, pi over 8, and then I just need to define s. Well, since I'm basically stretching from this parabola down to the axis, the distance between those is the function value. So 2 minus x squared dx. Well, because of symmetry, I can actually, sorry, this is supposed to be root 2 right there. I can, instead of going from negative root 2 over 2 to negative root 2 to positive root 2, I'm going to go from 0 to root 2. And I'm also going to pull the pi over 8 out in front. But when I multiply it by 2, it transforms into pi over 4. 2 over x squared dx. And that should be the sum of the infinite number of infinitesimally thin semicircular cross-sections that are perpendicular to the x-axis as they run from here, negative root 2, all the way through this to here, positive root 2. And because I don't want to waste a whole lot of time, let's go ahead and do this with our calculator. Sorry, I have to pull it down so you can't see the buttons because there's a light on this camera and otherwise it glares. So let's go ahead and go ahead and get that pi over 4 out in front. And I think you can do it without the multiplication symbol, but it's just a habit for me to put it in there. So 0 to root 2. And I know, let's go ahead and put an extra parenthesis in here because we're going to need it. X squared dx. And what that winds up giving us is 2.3695, or 2.370 if we round to 3 decimal places. Okay. Let's go ahead and do one more on this particular one, and then we'll move on to a second video on this. The third one is bound. But the base is x squared and 4x minus x squared. So that's 2 parabolas that intersect. And I want isosceles right triangles with the hypotenuse down. Now, while that may seem rather difficult, it really is not. Because let's think about what an isosceles triangle with hypotenuse down. Now you know that if it's isosceles right triangle, that these two sides are the same. Well, if they're the same, then that's that's obviously a right angle because it's a right angle, but that means that those are the same. And I know it's a 45, 45, 90 right triangle. But I also happen to know that an isosceles right triangle just happens to be a quarter of a square. So my area here is 1/4 s squared. Now I just have to figure out what my s squared is. Now this is y is equal, if you didn't actually get a chance to write it down because I moved it away too quickly, the downward facing parabola is 4x minus x squared. The upward facing parabola is my parent function, and I'm going to try and figure out the cross sections that are perpendicular to the x-axis and come up, and this is the hypotenuse, right? So whatever this is, I square it and multiply by 1/4, and then multiply by its width, which in this case is dx, and I basically have my volume of any one of the cross sections. But I don't want the volume of one cross section because it's roughly 0 because it's infinitesimally thin, right? I want to take the integral and accumulate all of them from 0 to 2. 1/4, that constant I'm going to put out in front. And then my s is obviously my top function, which is the downward facing parabola, minus the bottom function, which is my upward facing parabola, or 4x minus 2x squared. 4x minus 2x squared squared dx. So this is the 1/4, and this is the area of that triangular face. The dx is the width, which turns it into the third dimension and makes it a volume, and then I'm just accumulating the infinite number of those from 0 to 2 in order to get my integral. And from here, of course, I can, I could FOIL that out, and I could actually do that. It's a polynomial. It's not going to have anything weird like fractional coefficients or whatever. But for the sake of time, let's go ahead and do it in our calculator. 4x minus 2x squared squared dx. And boom, there you go, 1.06666666 repeated, okay? That kind of brings us to a close for this particular video. We'll do a couple more in the next video, but we'll also, either in the second or third video, stop for a moment and actually derive all of the formulas for the faces of the cross-sectional prisms that you're going to run into. And it'll just take a minute. We've already done the one for semicircles. We know the one for square. That's easy. We've done the one for an isosceles right triangle with its hypotenuse down. There's only a couple more that we actually need to attend to. So we'll get that here in the next video or two.